Hello everybody, my name is Michael and welcome back to my channel. Hope you're having a wonderful day so far. We're going to be jumping back into Harvard CS50X for 2025, more specifically into Week 1, Lecture 1 on C. In Week 0, or the previous lecture, we learned about basic computer science topics such as bits and bytes, how colors, images, and videos are processed and displayed to us, and given a basic introduction to some general coding principles such as functions, loops, conditionals, and booleans. And for our problem set 0 for that week, we completed a project in Scratch. If you want to get access to all my resources, including that problem set, please join my Discord where I provide that all. Link down below. Let's jump back into CS50X 2025 Week 1, Lecture 1 on C.
All right. So we are back and want to add one final flourish to this program because now, more so than a lot of the examples, like now the programs are starting to grow in length. And indeed, soon there'll be a few dozen lines of code, which is not uncommon. But let's suppose that we want to stop hard coding 3 everywhere and actually prompt the user for some number of meows here. Well, let me do this. In VS Code, I'm going to go ahead and get rid of this one line for now. And let's do something like this. Let's ask the user for an integer. So int, maybe n for number equals get int. And we'll say something like just number to give a number of meows. And then we'll go ahead and actually call meow, passing in not 3 this time, but passing in n. So we are using the return value of getInt to store it in a variable called n on line 8. And then we are passing n as the input or argument to the function called meow on line 9. And again, the actual implementation of meow on line 22 onward, like who cares, out of sight, out of mind, once it exists. We can sort of abstract it away mentally, but I'll keep it uptight here anyway. All right, so let me go ahead and open my terminal window, make cat /cat number. I can still type in 3 and it works. Or I can go ahead and type in 5, meow, 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 but it's not actually meowing 5 times.
I caught that bug we already found. It's right there in his function.
But there's a bug. Yeah, exactly. So the for loop, when I copy pasted it before break, I actually kind of got lazy and I forgot to change the 3 to an n so that it matches the name of the argument that's being passed into meow. So that was a bug, unintentional on my part, but we have now fixed it here. And now we are passing this in from main to meow. So if I make cat /cat and type 5 this time, I indeed get 5 meows. But it's worth noting there's some subtleties here in my code in that I've used n a couple of times. So this is actually deliberate that I've used n twice in this way to induce a bit of confusion. But it turns out this n is actually not the same as this n, nor this one. So what's going on here? Well, it turns out in programming, there's often this idea of scope. And long story short, generally speaking, variables only exist in the scope in which you create them. More down to earth, variables only exist inside of the curly braces in which you define them. So for instance, suppose I got a little sloppy, and suppose I didn't bother giving meow an input, and I didn't bother giving its prototype an input, and I just used n on line 14, because why? Well, I already defined n on line 8. So this is just an alternate universe in which I'm not changing meow to take input. I'm just using n in 2 different functions. In main, on line 8 and 9. Actually, I don't even need that. On line 8 and 9. And also, again, on line 14. This code will not work. Like, the compiler will not like this. Why? Because n does not exist inside of meow. Why? Per the heuristic I offered, n exists only inside of the curly braces in which it was defined, namely these curly braces here. So n is in scope in main, so to speak, but it is not in scope in meow. And that's why we kind of have to jump through these hoops and use inputs and outputs and inputs and outputs and pass things around among functions without sort of sharing things across functions instead. Now, I could clarify this and maybe change my argument here from n to like times. If I want to make clear that, oh, this is the number of times I want meow to be said, I don't have to use n for both. But just realize that if you do, it's just a coincidence. They are not usable in 2 different scopes. All right, let's do one other thing, though. Let's not only prompt the user for the number here. Let's make sure that it makes sense what number they give us. So if I do make cat, just to clean things up, /cat, suppose I type 0. OK, I suppose that's correct. If I say meow 0 times and it doesn't meow at all, that's arguably correct. But if I type in something like -5, it ignores me, which I guess is better than crashing or freezing or something. But like, ideally, it might be nice to handle this situation. And if they give me a negative number, prompt them again for a positive number. Prompt them again for a positive number. Like, make the program make sense. So how could we do that? Well, a couple of ways. If I go back into my code here, I could do this. I could maybe do something like a loop, or let's see. So if I get n, so if n is less than 1, then it makes no sense. So what do I want to do if n is less than 1? Well, I could just prompt the user again, and I'd say, OK, let's get n again. And then I can say, if n is less than 1, what do I want to do? I guess we could ask the user again. And then if n is less than 1, I could just, again, like I can give them like 3 tries, 4 tries to get this right. Like, this is obviously stupid. Like, I'm copying and pasting. I'm repeating myself. There's no end in sight. Like, I can't do this forever, surely. So this just feels like the wrong solution. So there are different ways to solve this problem. And funny enough, like a while loop is not really the best way. A do-while loop is, a while loop is not the best way. A for loop is not the best way. It turns out there's one other type of loop that we wanted to introduce that's super useful for getting user input, potentially again and again and again, so that the user cooperates. Specifically, what I'm going to do is this. I'm going to literally say do the following while something is true. So it's more of a mouthful. I'm spreading it out over multiple lines. But what am I going to put inside of the do block here? I'm going to say int n equals get int and ask for that number as before, close quote, semicolon. And I'm going to keep asking while, sorry, accidental enter, while n is less than 1 semicolon. So notice the semantics of this. Even though it's a little weird looking, it does read in English. Do the following, OK, get an int stored in n, and keep doing that while n is less than 1. But this code, as written, is not quite going to work yet. Let me try opening my terminal window, make cat enter. Oh, damn it. Like, use of undeclared identifier n. Well, here's where the line number is helpful. The line number is indicated here, 12, and it's repeated here, 12. So I clearly screwed up at line 12. So there's not that much going on at line 12.
Scope.
Why is n undeclared
It's not within these
in line 12, even though I literally just declared it in line 10?
It's outside the scope of these braces.
Exactly, because I declared n inside the scope of the do block, so to speak, inside the curly braces on lines 9 and 11. That variable n no longer exists by the time we get to line 12. It'd be great if it did, but it doesn't, because it violates that heuristic I proposed, which is that variables only exist in the scope of the curly braces in which they were defined. So how do I fix this? Well, it turns out you can declare a variable in advance outside of one scope, but then define it, that is, initialize it elsewhere. So the solution here is actually this. Inside of the loop, just set n equal to the return value of getInt. But per the heuristic, you've got to declare n, make it exist inside of the outermost scope of this function.
Okay.
So it's a little weird, and we're kind of breaking this down into 2 steps, but this is valid, recommended, correct C code. You declare a variable without giving it any value initially, and then in line 11, you proceed to give it a value, potentially again and again and again. Now, what's useful about a do-while loop? So a do-while loop, as the name implies, will do something no matter what. But it will potentially do it again and again and again while some question is true, like n being less than 1 in this case. All right. As an aside, why did we not do a while loop? Well, let's think about that. While n is less than 1, but wait a minute, n doesn't have a value. OK, so I guess we have to go back to doing getInt number colon semicolon. OK, but while n is less than 1, we're back to the same problem where we have to like repeat ourselves again. So this is why for loops, while loops, not the right solution when you want to do something at least once, but potentially again and again. So the right solution here again is this new and final looping construct. I'm just hitting Control Z a lot, whereby we've done it as follows. All right, let's try this. Clear the screen. Make cat, enter, /cat. Let's type in 5. Still works. Let's type in -5. And notice it doesn't just ignore me. It prompts me again and again and again. Even if I type in 0, I've got to at least give it a positive integer. Well, this actually seems like kind of a common paradigm. Like, what if we want to prompt the user for a positive number in other programs too? You know, we're nearing the point already, even after just week 1. It'd be nice to like write our own reusable functions that solve common problems. And eventually maybe we can put them in header files as well. But for now, let's go ahead and do this. I'm going to actually copy all of this code, and I'm going to create one more function in this file below main called getPositiveInt for integer. And I'm going to specify that it doesn't need any inputs, because the only thing this function is going to do is that exact same thing. So notice that I've just moved my code from main into a function that's name describes what it does, getPositiveInt. I'm declaring n here. I'm doing this again and again, and I'm doing that while n is less than 1. And what am I going to do up here? I can do something like this. Give me a variable called times, for how many times do you want to meow, and just call getPositiveInt, semicolon. So now, again, we've abstracted things away. And just like in Scratch, our final example, which looked a little something like this, where we just called a function to meow 3 times. Now we're calling a function to get text. If I hit enter an arbitrary dramatic number of times, out of sight, out of mind, I now have 2 functions in this world, getPositiveInt and meow, that are collectively implementing this entire program. But it's not quite correct. There's one mistake here still. Notice that getPositiveInt is written slightly differently from the meow function. And just to be clear, too, let me copy its prototype to the top of the file, just so we don't make that same mistake I made earlier where I didn't put the prototype at top, so C didn't know what it was. What is different about these 2 prototypes at a glance? Yeah. OK, so getPositiveInt apparently, and we've not talked much about this, apparently does have an output of type integer. It's supposed to return an int, hand me back an int. It doesn't have any input. That's what the void in parentheses meant. No input, but yes output. And meow, funny enough, is the opposite. Yes input, no output. Why? Because it has a side effect, the visual thing, where it prints something to the screen, but doesn't hand me any useful value back like the ask function or the ask puzzle piece did. So these are sort of opposite in functionality, which means I actually need to return an integer from this function to whatever function wants to use it. So if I want the assignment operator to work here on line 9, I need to do what all this time getInt, getString, and other CS50 functions have been doing. I need to, in my own function, return that value, literally with a new keyword called return. And this is why I keep sticking out my hand. When you want a function to hand you back a value, you literally use return and then that value. That's why we have return value as a term of art, literally the return keyword. So if I open my terminal window now, make cat, enter, I did screw up accidentally.
Times.
How? Yeah.
I already caught that.
Yeah, so on lines 9 and 10, I made a quick change. I changed my variable to times, but I stupidly didn't change this. So that's fine. That's why n was undeclared in that context. Let me clear my terminal, make cat once more. OK, that worked. /cat. Let's type in 5, and it's still working. So again, even though the code feels like it's, even though the code is kind of growing and growing and growing, it's the exact same program we wrote super simply before break. But now we're sort of modularizing it. We're creating reusable functions. And this is why functions like getString exist, getInt exist. Like CS50 wrote those years ago. And we realized, why are we copying and pasting these functions in all of these different CS50 programs? Let's factor out that functionality into a function of our own, getInt, getString, just like here I'm proposing to factor out this functionality, get a positive integer that gives you even more precise functionality. So theoretically, you could use and reuse it in other programs too. By not even just putting it here, we could go put it in a file of your own name and include it in future programs as well. Like that's all a library is. Someone realized, geez, other people, including myself, might find this function useful again and again. Let's package it up in our own custom functions, just like our custom meow puzzle piece last week, so we can indeed use it again and again. And the takeaways for now is that unlike Scratch, which was a little more user-friendly, in C, you have to specify if you want your functions to have inputs, and you must specify if you want them to have outputs as well. But more on that syntax to come. So where does that bring us? So after all this discussion of code, at the end of the day, this is what's important in the world of programming. Not surprisingly, it's what's important when it comes to grading and evaluating the quality of code. One, and first and foremost, is correctness. If the code does not do what it's supposed to do, what was the point of writing the code? So correctness sort of goes without saying. Design, again, is much more qualitative. It's like getting feedback again on an English essay. Where reasonable people might disagree, you can make your argument better, you can structure the paper better, you can structure the code better in the case of programming. And style is purely aesthetic. Does it look good? Is it pretty printed, so to speak? Can other people, colleagues, future, and classmates present actually read and understand it? That's what we mean by style. Nicely enough, within CS50's programming environment, you will have tools to evaluate the quality of all three of these axes, so to speak. So in problem set 1 onward, you'll be introduced to a command line tool that you type its name at the prompt called Check50 that will check for you the correctness of your code. Not necessarily exhaustively, like there might be mistakes you've made that we don't catch, which doesn't make your code correct, but it is a tool for finding many of the mistakes in your code. In the real world, you would have colleagues or yourself would write tests for code you wrote or someone else wrote. So like testing code is not just a grading thing. It is a real world thing to ensure that systems are designed correctly. We saw the Style50 tool in VS Code already. You click the Style50 button. There is now, thanks to the duck, a Design50 button too, also in that top right-hand corner, whereby once your code is correct and working, like several of my programs have been, you can click Design50 and the duck will not just quack, but give you qualitative advice, if it can, on how you can make that code even better, even before you submit. And of course, there's all of us humans in the room and online that you can ask these same questions of as well. So let's now solve some sort of real world, but still simple problems as opposed to emphasizing small bite size as we have thus far. So the first of these programs falls into this category of having side effects. So let's implement one or more functions that takes an argument's inputs, and as its output produces these visual side effects. We'll draw inspiration from Super Mario Brothers, not surprisingly perhaps here. The original one, which was very two-dimensional, side-scroller, left to right. Mario or Luigi move from left to right and generally have to like jump over things like pyramids or other shapes on the screen. So how might we go about implementing some of the screens from Super Mario Brothers, albeit textually? Well, we'll make it a little black and white and ASCII art, so to speak here, using just our keyboard. But suppose we want to write a program called Mario.c that just prints out 4 question marks. It's not going to be nearly as pretty as what's on the screen here, but the logic is going to be the exact same as what Nintendo presumably did years ago. So let me open VS Code, my terminal window. Let's code a program called Mario.c. In Mario.c, I'm going to kind of start with some boilerplate. I know I want to print, so even if I don't know how to do this yet, I'm going to include standard io.h. For today's purposes, I'm going to copy, paste, or type out that same line again and again, int main void. And inside of my main function, akin to the green flag being clicked, I want to go ahead and print out 4 question marks. Well, honestly, the simplest way I can think of doing this is with printf, question mark, question mark, question mark, question mark, maybe a \n to move the cursor, and that's it. So that is arguably correct. So let's do make Mario in the terminal, /Mario, and it's not quite as pretty as the game version of it, but it is in fact the exact same idea. But here's sort of an opportunity, a stepping stone to do better design. Like this game changes over time, and not all of the screens have just 4 question marks. It might be 5, 6, or even more. So what's the right programming construct with which we could generalize how many question marks are printing here? Like what feature of C do we want? Like a loop, like a for loop, a while loop, or something like that. And there's different ways to do this, but honestly, I've proposed earlier that we get into the habit of reaching for loops as just very conventional. So let's do that. For int I equals 0, I less than 4, because that's how many I want for the moment, I plus plus, and then inside of my curly braces there, let's go ahead and print out, quote unquote, a single question mark, but no new line. Let me now go ahead and make Mario. And can you anticipate a arguably aesthetic bug when I hit enter? It's not going to move the cursor to the next line. But the solution here is a little non-obvious. I don't think this helps me. If I put the \n there and I do make Mario again and /Mario, what is this output going to look like instead? Yeah, like a vertical column of question marks, which, while nice enough, is not the goal at hand. The goal is these horizontal ones. Right. So someone else, what's the fix here if clearly putting the \n inside of line 7 is wrong?
Print another line.
Yeah, so put it after the loop, and not after the printf line specifically, after and thus outside of the loop, so that after that loop is finished executing 3 total times, it's totally fine to just print nothing other than a \n, so long as we now recompile the code, make Mario, /Mario, and voila, now we have 4 in a row. It's a little generalized. OK, so we've sort of plucked off a fairly easy problem. Well, let's go back to the world of Mario and try something that is, in fact, vertical like this. So this is another scene with like 3 bricks here. Instead of using question marks, we'll use hash symbols to represent bricks. This actually is the incarnation of my mistake a moment ago. So let me undo this by getting rid of that printf. Let me change the inside one from a question mark to a hash symbol, which looks the most similar in ASCII to a brick. And let's go ahead and put in \n after that. If I do go ahead and do make Mario, /Mario, it's not that interesting, but, and it's actually not that correct because I wanted 3, so no big deal. I can, of course, go back to my code and change the 4 to a 3, or better yet, I could use getInt or my new getPositiveInt function and just generalize this further so that I can print out any number of them. But for now, /Mario gives me 3. All right, so we've plucked off the second of 2 problems. Let's now let things escalate a bit. So it turns out once you get to like world 2 and beyond, there's some underground parts of Mario where you actually have bigger, more solid bricks like these here. And just by eyeballing it, this is like a 3x3 grid of bricks, like 9 of them total, we'll conjecture. So how can I go about implementing this? Well, now is where the program gets a little more interesting. And the sort of not correct, well, the poorly designed way to do this would be like printf ### \n semicolon, and then maybe printf. Like that's kind of like correct, but not well designed. So make Mario /Mario. You know, it doesn't look like a square just because these hashes are more vertical than they are horizontal, but it is correct, this example. But it's not very generalizable, and this is like literally hard coding. I copy pasted. I'm just doing a lot of bad practices here. So what could I do instead? Well, it turns out we can combine today's ideas, including loops, to do things again and again. So what is this grid of bricks? It's a 3x3. So that's like, you know, it's like a row and a row and a row. And then within each row, there's like column, column, column. So it too is like an old-timey typewriter that sort of prints one line, then the next line, then the next line, and so forth. So how can we conjure that in code? Well, let me go ahead and do this. I think a print approach would work is like this. For int I equals 0, I less than 3, I plus plus, because I know I want to do something 3 times. But what do I want to do 3 times? This loop kind of represents in my mind's eye row, row, row. So in fact, I could be more pedantic. If I want my I to mean something beyond int, I could say row equals 0, row less than 3, row plus plus, just to help me think about it. And then what do I want to do on each row? What do I want to print? Like column, column, column. So brick, brick, brick. So how do I print 3 bricks or any number of bricks? Well, I could kind of cheat and just do printf ### \n. But again, I can't generalize. I can't take an input from the user and print 4 or 5 or 6 bricks. So that's going to get me into trouble eventually. So maybe I could use a loop. So I could do like for int I equals 0, I less than 3, I plus plus inside of my loop. And then in here, I could print out 1 hash. And that's kind of on the right direction, the right path, because now I'm just using the simple building block or brick, but reusing it again and again. And it's totally fine to have nested these columns in this way. I used I out of habit, but what would a better name be? Well, maybe column, or maybe just COL, call for short, so that my code is sort of saying what it does for me. And I don't have to use row or column explicitly. I don't need to print them, but I am using them as counters, one after the other. So let me go ahead and run make Mario /Mario. And I'm feeling good about this, but damn it, there's 9 bricks, but they're not really laid out right. Why? What's the fix? Yeah. Yeah, I never went to a new line. And let me do what I think you're not going to suggest I do. Let me just go to the obvious place. All right, well, let's put one right after the brick. But of course, if I do make Mario /Mario, I'm making the same mistake as before. I'm printing out too many new lines. So in between, what lines do I actually want to print a new line? Between, yeah. Yeah, so 10 and 11. So outside of the inner loop, but inside of the outer loop. So it happens again and again. So let's just print out as before a single \n semicolon. Now let's do make Mario /Mario, enter. Now it's generalized as I see fit. And if I really wanted to dwell on this, I could go in and I could prompt the user with getInt or with getPositiveInt, figure out what row and or column should be. We can make any size brick that we want. but now we have sort of a nice starting point. But there's another way to think about this, because I dare say, especially for like your first CS50 problem set, if you're trying to print bricks in the world of Mario in this way, it's probably not going to be obvious to come up with loops like this and just magically get it working after like 45 seconds in total. Like, it'll be a struggle at first, but there are some patterns to follow. So one, it's pretty conventional, nonetheless, to use just I, and then J, and then K, and then L. And if you've got nested, 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 nested for loops, at some point nesting, you're probably writing bad code. It's not well designed. But 1 or 2 or maybe 3 nestings could be an OK thing. But you cannot use and reuse I again and again. Why? Because if you're counting I here, but then you're changing I here to do your columns left to right, you're going to get all of your math out of sync. So you need 2 separate variables. I and J are conventional, or row and column would work too. But if we go back to this idea of rows and columns, well, let me actually factor something out here. And this might help you instead. Suppose that you set out on this problem. You know you want to do something like 3 times, but you don't quite understand how to print those rows. Well, take a baby step, a bite out of the problem, and maybe do this. Create a function with no output, just a side effect, whose purpose in life is to print a row. And how many rows? Well, maybe n for some number of rows, for some number of bricks, rather. How do you print a row of bricks? Well, let me just think about this in isolation. How do I print a single row of bricks? That's easy. For int I equals 0, I is less than n, if I'm generalizing, I plus plus, and then, whoops, I plus plus, and then inside of my curly braces, go ahead and just print out a single hash, and at the end, as you suggested, print out a single new line. In other words, abstract away the idea of printing a single row. And in fact, at this point in the story, especially if you're struggling to get started, you don't even need to start with main. Like, take a bite out of the problem that makes sense to you, that's smaller than the whole problem, printing a single row. Because then you can come in and iterate. Then you can go in and say, OK, now let's write my actual main function. So int main void, as always. And now what do I want to do? I want to print out a whole bunch of rows. How do I print out a whole bunch of rows? Oh my god, it's like the same idea. For int I equals 0, I is less than, let's call it 3 for now, but we can generalize that, I plus plus. And what do I want to do on each iteration of this loop? My gosh, just print row with 3 bricks. And then we're sort of done. Right? Again, out of sight, out of mind. This function can go away and never be seen before, because once print row exists, that's what it in fact does for me. Now, this isn't 100% correct. I still need my prototype, because if I've made my own function, I need to tell C in advance that it shall exist. So I need to copy and paste that one line of code. If I were really being pedantic, this is bad design. In general, when you have the same number in multiple places in a programmer would call this a magic number. Like, how is that working? Like, you're just an honor system that you're using the same number again and again. So a better solution here, even if you're not going to take user input, would be to do this. Int n equals 3, and then use n here, and then use n here. Or you could call it anything you want. But now you've specified 3 in one and only one place. And we can go one step further. It turns out in C and in other languages, you can protect yourself against yourself. If you know that a variable should never change its value, it should always stay 3 in this case, you can use what's called a constant, where you can specifically say, I don't want just n to be an int. I want it to be a const int. Const for short, for constant. And this means even if I try to change n in my code, the compiler will not let me. So I can protect myself from myself. Or in the real world, you can use a variable that none of your colleagues can foolishly change on you without you realizing that it has happened. So a lot of programming, honestly, is just not trusting yourself the next morning when you've forgotten what code you wrote, let alone the next month, the next year when you're writing code in the real world. So constants just give us a feature to defend against ourselves. There's another feature that's useful too, especially when you wake up the next day and you're like, oh my god, like how does this code work? What does it do? Well, there's comments in code. And some of you might have used this in Scratch. You could add little yellow sticky notes in Scratch for comments. In code, you can do something like this. You can, if you want to put an English reminder to yourself, or if you speak some other human language, a comment in Spanish or any other human language, you can write it with a / at the start of the line. And then you can say something like print n rows. And then this tells you in a comment what those subsequent lines of code are doing. It's sort of a note to self. It has no functionality for the computer's sake. It just is a note to yourself. Or you can say something like this, like never change n, because you're making clear that it's indeed constant. But that, too, is a little pedantic since const says the same. But comments are notes to self to help you remember what something is doing or why you did it this way. All right, so one final set of examples that push the limit of what computers can actually do. Thus far, we've solved every problem I proposed. But that's because I've kind of been skirting some of the underlying challenges. So it turns out that we have not only functions that give us side effects, like visually on the screen, we again have functions that have return values. So let's focus on those and where things can go wrong. And let's use a bunch of other operators as well. Suffice it to say, computers got their start by being really good calculators. So computers support addition, subtraction, multiplication, division, remainder operators, represented by the percent sign here, which says take the remainder of something over something else. And there's even more operators than this. So let's go ahead and implement our own calculator of sorts that actually has some bugs along the way. Let me go back over to VS Code here. I'll close mario.c, open my terminal, and code up one final file called calculator.c. And in this calculator file, let's go ahead and do something super simple initially. Let's go ahead and include cs50.h. Let's include standard.io.h. Let's do int main void as always, all boilerplate thus far. And now let's do something more interesting. Int x equals getInt, and we'll prompt the user for an x value. Int y, prompt the user for a y value, as we've done previously for comparing numbers. And let's just do something super simple. Let's give myself another variable, int z equals x plus y. And then let's print out the sum. So printf, quote unquote, and I don't want %s here. If I want to print out a number, someone said it earlier, we want %s for string, but %i for integer, \n, and print out the value of z. So it's a little silly, this calculator. It just adds two numbers together, but it's going to demonstrate some points. So make calculator, enter. So far, so good. /calculator. Let's just say x is 1, y is 2, z is going to be 3. This code is correct, simple though it is. Is there an opportunity for marginally better design? Could we tighten this up, make it shorter? Fewer lines means lower probability of bugs, probably? Yeah. Yeah, we don't really need a separate variable z. I mean, it's fine if it's clearer to you, if it's clearer to your TF, if it's clearer to your colleagues. But honestly, this is so relatively simple. I think we just get rid of z and just say something like x plus y here, which is totally reasonable as well. But you don't want to take this to an extreme. Heck, if we don't need z, do we really need x and y? Well, we could do something like this. Let me actually delete these lines of code and claim we can do this all in one very pretty one-liner. We could do, say, getInt x plus getInt y. And notice now, kind of like the join example last time, I'm calling getInt once, getInt twice. Both of them return a value, which is going to be 1 and 2 respectively, based on what I typed earlier. Then I'm doing 1 plus 2. That's going into printf as the second argument. This is actually correct and will work. It's just stupid. Don't do this. We've crossed some ill-defined line where this is just harder now to read. And so even though the variables aren't strictly necessary, I would argue, and I think most programmers would argue, this is just much more readable. Each line is doing a little bit less work. There's less chance for error. It just makes a little more sense. But reasonable people will disagree. So therefore, this is to say over time, too, you and your TF might disagree. You and your colleagues might disagree. And at that point is when the sort of religious debates kick in as to which way is the right way. All right, so that's one calculator. Let's do something else that maybe just doubles a number here. So let me change this to just get one integer from the user. Let's just call it x. And let's just double it quite simply. So printf. %i\n x times 2. We'll quite simply double it. The star operator is indeed multiplication in this case. So that's going to go ahead and double my number. So make calculator again, /calculator, enter. And let's go ahead and type in 1, and I get back 2. Let's run it again. Type in 2, I get back 4. Type it again. Let's type in 3, I get back 6, and so forth. All right, so that's not bad in this case here. But what if we actually want to write a proper program here? In fact, yeah, let's see. This is a sort of a meme that comes and goes. Let me see if you recognize this. I'm going to go ahead and say another variable, not x. Let's be more specific, like int $=1. And then let me deliberately induce an infinite loop. Sometimes it is useful to induce an infinite loop so long as you eventually break out of it somehow. If you don't want the program to run forever, I'm going to ask the user a question asking them for a char c using get char. And I'm going to ask them, quote unquote, here's %i period, double it, and give it to the next person, question mark. This is ringing a bell. And then we can pass in to getchar the dollars value there. So actually, this looks a little cryptic already. I'm going to put a $sign in front of it as though we're actually dealing with US currency. And what do we want to do? How about if the user says y for yes, double it and give it to the next person, then let's go ahead and do dollars, and let's double dollars. So I can do dollars equals dollars times 2, or recall the trick for plus and minus. I can also do times equals 2, which just doubles it in one line as well. Just little syntactic sugar, as programmers call it, that just tighten up your code, even though it's the exact same thing. But what if the user does not type y and they want to keep the money? Well, we have an else condition. At that point, you don't want to keep asking them with getchar. Let's just break out of this loop instead. So break is another keyword that if you're inside of a for loop, a while loop, a do while loop, you can forcibly break out of the loop early if and when you want to. And so this sort of satisfies the goal of making sure that this doesn't run forever, but it is going to run again and again and again while we keep prompting the user with this question. So let's see now what happens, except at the end, let's go ahead and make sure the user knows like how much money they're walking away with. Here's $%i \n $. So we will see at the end of this whatever dollar amount the person ends up with. Make calculator, enter, /calculator. And let me increase my terminal window size. So here we go. Here's $1. Double it and give it to the next person? Yes. Here's $2. Double it and give it to the next person? Yes. 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 So, you know, the Instagram reels aren't that long, but if like you keep doubling it again and again, this is called exponentiation, which will make you quite wealthy quite quickly, because notice we're already in the thousands of dollars by just saying yes and yes and yes. It's an interesting sort of societal question as to what dollar amount you would keep the money and no longer double it and pass it on. But for now, we'll just keep doubling it because this is just getting bigger and bigger, seemingly infinitely large in the C program. But oh my God, like apparently the Instagram reels cut off the meme too short because eventually it goes negative and then right? 0. Like what's actually going on here? Like the code is actually correct, but we're bumping up against a different kind of problem. Any instinct for what is actually going wrong here? It's not doubling forever. Yeah. Yeah, there's not enough bits to store bigger and bigger numbers. Recall with 32 bits, which happens to be how big most ints are, you can count as high as 4 billion if you start at 0, or roughly as high as 2 billion if you want to handle negative numbers as well, negative 2 billion to positive 2 billion. So eventually, once I get to like $2 billion or $1 billion, it goes negative, and then it just goes to 0 altogether. This is because of something called integer overflow, whereby if you only have a finite number of bits, and you keep incrementing them, eventually you can't just carry the 1 because there's no 33rd bit. So all of the other bits wrap around from 1s to 0s, and it looks like all 32 of your bits are 0 because the 33rd bit was supposed to be the 1, but it's not there. They don't have enough memory. So this is a fundamental problem with computers whereby if you count high enough, things will just start to break, at least if you're using C or C++ or certain other languages that don't anticipate this. And there's a very real implication of this. So here's a photograph of something we'll look at more in time to come, like of memory inside of your computer or phone or any electronic device. Suffice it to say, there's only a finite amount of memory, and if you're only using 32 bits then, or heck, even 3 bits, you will eventually overflow. We used 3 bits last week, so here's an example. In binary, if you're only using 3 bits per the white digits here, I've put in gray the 4th just to show you what carry we might want to have. Here's 0, 1, 2, 3, 4, 5, 6, 7, just like last week. And just like last week, someone said, how do we get to 8? We need another bit. But if that bit is grayed out because it doesn't exist, we've just overflowed this tiny integer and gotten back to 0, just like my money went to $0 instead. So how do we actually avoid that? You know, one way to do this is this. Let me hit Control-C to break out of the program, or I could just type no. Let me shrink my terminal window and clear it here. I could actually do this. It turns out that ints use 32 bits typically, but there's another data type that was on the slide before called long, which is a longer version of an int, which is 64 bits, which is crazy big. There's not that many dollars in the world, but it's still finite, even though I can't pronounce a number that big. But if we change all of our ints to longs, and we change our placeholder from %i to %li for long int, I can actually count higher and higher. So case in point, let me actually go back to my terminal, make calculator, enter, make it larger again, /calculator, and I'm just going to keep saying yes, but faster this time. The sequence is exactly the same, but recall that once we got into the billions, it started to wrap to negative and then 0. This is a lot of money now. Like, longs are indeed longer, and I could do this probably all day long. Oh, interesting. No, I shouldn't have said that. Can't do this all day long because eventually a long 2 will overflow. I just didn't think it was going to happen that fast. So a long 2 will overflow because we'll need a 65th bit, but the computer has not allocated it. So that too becomes an issue of overflow. To read an excerpt, like, these are very real world issues. And in fact, here's a photograph of a Boeing 787 years ago that actually had issues beyond the most recent issues with Boeing airplanes, whereby after 248 days, the Boeing 787 years ago can lose all of its electrical power due to the generator control units simultaneously going into fail-safe mode, whatever that means. But if you dig into this, it turns out that there was a software counter in these airplanes years ago that would overflow after 248 days of continuous power. 248 days, why? Well, Boeing was using a 32-bit integer, and they were using it to count tenths of seconds. And it turns out if you do the math, after 248 days, you have used too many tenths such that you overflow the size of a 32-bit integer. The plane would essentially have this integer, this tiny, stupid little variable, overflow. But generally speaking, when your numbers suddenly go negative or 0, bad things happen. The plane could literally lose its power mid-flight or on the ground. And if you can believe it, anyone want to guess what Boeing's workaround was till they fixed the actual software?
Turn it off. Bypass
What's that? Not even reboot the plane. Like, they were told every few days, certainly every 248 days, turn the power off, turn it back on, which stupidly is what all of us have been told for years with our Macs and PCs and phones. Why? Because sometimes, because of bugs in software, computers get into funky states, which is a colloquial way of saying, like, some programmer made a mistake and some counter overflowed or some condition wasn't handled and just weird, unexpected things happen. So rebooting just resets all of your variables back to their original values and sorts of gives you more time, more runway in this case, no pun intended. There are others. In fact, one of the most famous ones from like the 1980s was the original Pac-Man game. Only had support for 255 levels. Why? They were using 8 bits. Recall that 8 bits gives you 256. But if you start counting at 0, you can only go to 255. So the crazy kids who were so good at Pac-Man that they got to level 256, the makers of Pac-Man did not anticipate that anyone was going to win that many levels, and just weird stuff happened on the screen. All of the fruits sort of started overwriting everything because they didn't have enough memory allocated to the level, nor did they have a condition that says if level equals 255, you win. Like, there was just nothing handling that corner case, so to speak. So these things abound even these days. Thankfully, in some languages, there are better solutions where you can use big integers, and you'll just use 64, maybe 128, maybe 256 bits, but you need to use a language or a library that allows you to grow and shrink the amount of memory being used, and many, if not most languages, do not do that for us. So there's a few final problems to see that we've been taking for granted thus far, and they also involve numbers and memory. So let's go back into our calculator. Let's throw away all of this meme code here. And instead, let's go ahead and do something simple again. Int x equals get int and prompt the user for a variable x. Int y equals get int, prompt the user for a variable y. And this time, instead of addition, instead of doubling, let's do division. So printf, quote unquote, %i\n, and then plug in x divided by y. So use a single / for division. Let me go ahead and make calculator down here, /calculator. And let's go ahead and do 1 divided by 3, which should in fact be, well, it's not really 0, right? It's like 0.333. Let's try this again. How about /calculator? 3 divided by 2 should be 1.5. Nope, computer thinks it's 1. Well, what's happening here? Well, it turns out when you're using integers in a program, you are vulnerable to what's called truncation. An integer plus an integer gives you an integer. An integer divided by an integer, funny enough, gives you an integer. So even if the answer is supposed to be 0.333 or 1.5, everything in the world of integers throws away the decimal point onward, and you only get the integer part of the value. So it's not even rounding, it's truncating everything after the decimal. So this program is just not correct, but there are solutions potentially. For instance, if I go back into my code here, and I use a different format code we haven't used yet. We had S for string, I for int. There's also F for float. And a float was like a real number, something with a decimal point in it by definition. We just haven't used it yet. I could tell the computer to print this as a float. So let me do make calculator again. And now it's specifying type double. There's an error here. The problem is that I can't just tell the computer to format this number as a float. I need to convert the number, x divided by y, to a float. And I can do this in a couple of ways. One, I could literally change all of this to floats and just avoid the problem altogether. Use float, use get float, use %f, and I'm done. But if I want to use ints for whatever reason, because I want the user to type in integers, but I want to show them real numbers with decimal points for correct math, I can do what's called casting a value. I can, in parentheses, which is a weird new use of parentheses, I can say, hey, computer, please treat the following integer as a float instead, thereby avoiding truncation. Do not truncate for me. So if I now run make calculator again, /calculator, and type in, for instance, 1 for x, 3 for y, now I get an actual floating point value. I'm formatting it as such, and I'm telling the computer to actually arithmetically calculate it as such as well. But here, too, I'm kind of cheating you of a reality. It turns out, let me clear this screen here, and it turns out that there are fancy ways in printf to tell it how many digits to show you, how many significant digits. And the syntax is very weird. I have to look it up constantly. But instead of just saying %f, you literally put some numbers in between there, and you say 0.5. And that will say, it's weird syntax, hey, printf, format this to 5 digits instead. So let me go ahead and do make calculator again, /calculator. And let's do 1 divided by 3. And indeed, I get 5 significant digits there. But suppose I get a little crazy and I want 50 significant digits. Well, according to grade school, I should just see more like 3s. But watch this. Make calculator, /calculator. And it turns out that whoever taught you grade school math was kind of telling you some white lies. Because if you really do it with a powerful Mac or PC or phone, 1/3 is actually 0.33333334326744079. Who's right? Mr. and Mrs. So-and-so from grade school, or like
No, I think the floats do some, and the floats have some
What's going on here?
that aren't super accurate to math, I don't think, right?
What explains this? It all comes down somehow to weak zeros, zeros, and ones. Why is this floating point number imprecise, so to speak? What's the intuition? Yeah.
Can't have half on, half off bits.
Yeah, similar in spirit. Just as ints only use 32 bits, floats also use only 32 bits. If you want more, just as int has long, floats have something called double. So I could kind of avoid some of the problem by switching to double, but that's still going to be finite. And if you think about this intuitively, if you're using a finite number of bits, be it 32 or 64, you can only represent literally so many patterns and thus so many floating point values, so many real numbers. But how many real numbers are there in the world? Like literally infinitely many is the challenge of real numbers. You can just keep adding numbers after the digit. So how could a computer, Mac, PC, or otherwise, possibly represent every floating point value super precisely if there's not enough patterns to represent every number in the world? Moreover, the way that computers use to represent numbers sometimes do not allow them to represent numbers so precisely. We can get more significant digits maybe, but not 100% perfection or precision. So floating point precision, too, is a fundamental problem with computers today. And unless, again, you're using a specialized language or library that understands for scientific computing the implications of overflow or imprecision, your code will have mistakes, much like Boeing discovered, much like Pac-Man discovered as well. And in fact, just to end on a gloom and doom note, it turns out there's another problem like this on the horizon already. So back in my day, everyone was really worried about the Y2K problem, the year 2000 problem. Why? Because for decades, when computers were invented, most systems were using just 2 digits, independent of bits, 2 digits to represent years. Why? Computers came out, a few decades ago. Who'd think that a computer is still going to be running decades later? Turns out they were, especially in government and corporations and the like. But if you're only using 2 digits to represent years, and the millennium comes around and it's 1999, about to roll over, what comes after 1999? Well, if you're only using 2 digits, ideally 2000,
00.
But if you're only using 2 digits, the year 0 comes after the year 1999. And the whole world, truly, you can look it up nowadays on Wikipedia, was freaking out because there was so much old software in the world that could have had this mistake. And who knows, planes falling out of the sky, computers rebooting, freezing, like no one really knew because this was an unhandled situation in code. So thankfully, the world actually got its act together. The world did not end in the year 2000, and most systems were updated in time without crazy horror stories. But we're going to have this happen again, because it turns out, just a few years from now at this point, computers for years have been using 32-bit integers to keep track of time, in the sense of like what time of day it is. And the point in time they decided years ago was, hey everyone, let's just keep track of how many seconds have passed since January 1st, 1970. And we can relatively compute time anytime thereafter. So that's great. That gives us a lot of decades worth. But 32 bits eventually maxes out at like 4 billion positive, or 2 billion if you want negative and positive. And it turns out if you count the number of seconds between 1970 on up, on the day January 19th, 2038, the world might again end because all of these clocks are going to overflow. And we're going to end up in the year 0 or negative something. Now, what's the solution there? I mean, my God, it's the exact same thing. Like, stop using so few bits, use more bits. But bits and memory and computers used to be expensive. Nowadays, storage is so much more available. But among the things we'll discuss then is how you can throw both hardware and software at this problem. But for now, maybe set a Google Calendar reminder for January 19th, 2038. And hopefully, we'll see you next week.
All right. We finished it.